Let's calculate the double integral of in omega of x, where omega is the set of numbers where x and y are from the set of real numbers, r squared, and where x squared plus y squared is smaller or equal 1, and where y is bigger or equal x. When having a double integral, what we have to do is knowing what we're integrating in, that is, knowing the set of numbers we are integrating. So this expression x squared plus y squared can be written as x minus 0 squared plus y minus 0 squared equal 1. And as you should know, this is a circumference with the center in 0, 0, the origin, and with radius 1. Let's draw it up here on the right. But as we're told, smaller or equal 1, they are just the points x and y, which it's the distance to the point 0, 0 the distance is smaller than 1. So that would be calculating the what's inside the circumference, not the outside. And now let's have a look at the y bigger or equal 1. As we know, having an expression of the type like this, y equal x, is having just a straight line, because our value for x is the same value for the y. So this would be our straight line on the graph up here. It goes through the point 0, 0, 1, 1, 2, 2. So the circumference and the straight line tells us where we're integrating on, that is the group omega. We know that we have to integrate the interior of the circumference. We're calculating this, but what we're doing with the straight line, let's draw up here in green. What we're calculating of the part we're calculating of the circumference, this would be the part, the superior part, the upper part of the circumference, and this would be the second part of the circumference. And for knowing which part we have to calculate, let's try substituting some points. Let's go with a point 1, 0. Is this point 1, 0 from the group omega? We know that this point is already from the circumference 1, 0, because it is on the perimeter of it. And now let's try if it obeys to the condition that y has to be bigger or equal to x. We can see that 0 is not bigger or equal 1, so the point 0, 1 is not from the set of omega. And what does that mean? That means that we are not integrating all the numbers that are not from the group omega. So we're just integrating the upper part of the circumference, not the red part, just the green one. Now let's go with the integral. We can see that we're integrating the interior of a circumference with a straight line as a condition. And for doing this, we will express the circumference in polar coordinates, because it is going to be much easier in doing it this way. So expressing this in polar coordinates, we would have the polar coordinates are x equal to r times the cosinus of theta, and y equal r, the radius, times the sinus of theta. So we have r the module and theta the argument, and our set of numbers omega, we have it up here, and we can see that the points are interior to the circumference of radius 1 and center of on 0, 0. So the set of numbers we're integrating is from 0 to 1, that is the interior of the circumference from the center 0 to the point 1, because it has radius 1, of course. And now let's have a look at what the straight lines tells us. We can see that integrating this, we'll have to integrate from pi quarters, that's 45 degrees, to until minus p quarters. That would, so it would be from pi quarters until 180 degrees plus p quarters, that's pi 180 degrees plus p quarters. Calculating this, we would have 4p quarters divided by 4 plus pi quarters. That would be equal to 5 times pi divided by 4. So the argument goes from pi quarters till 5 pi divided by 4. Now let's change the function x, that is x is equal to the radius times the cosinus of theta, and now we have to multiply it by the Jacobian of the transformation into polar coordinates. In other videos, if you look for changing into polar coordinates, you will find how to calculate the Jacobian of this transformation, but we're not doing it here. I'm just telling you what it is. That is just multiplying by the radius r times the derivative of the radius and the derivative of the argument. Let's erase this down here and let's calculate this integral we have. So we can choose if integrating it first from the radius or the argument. Let's go first with the argument, and theta goes from pi quarters to 5 pi quarters. So as we're integrating in two variables, we'll have inside here the cosinus of theta, and if as the r doesn't depend of theta, let's write it out of the integral as r squared, because we have r times r, and inside a parenthesis the derivative of theta, and outside the derivative of the radius, the integral, I'm sorry. And now let's calculate down here the integral of theta. That is very easy, it's just the integral from pi quarters to 5 pi quarters, the cosinus of theta. This is the cosinus, the integral, it is the sinus of theta between 5 pi quarters and pi quarters. So this is the same as the sinus of 5 pi quarters minus the sinus of pi quarters. Operating this, we would have the sinus of 5 pi quarters. As we are on the third quadrant, the sinus is negative, so we have minus the square root of 2 divided by 2 minus the sinus of p quarters, that is the square root of 2 divided by 2. And From here we would have minus 2 times the square root of 2 divided by 2. That can be simplified, and it can be written as minus the square root of 2. So let's write it up here on our main integral, and we would have the integral from 0 to 1 of r squared times minus the square root of 2, and as minus the square root of 2 is a constant, it can be written out of the integral. So our integral would be from 0 to 1 of r squared, and this is very easy. The integral of r squared is r cubed divided by 3 between 1 and 0. That is equal to minus the square root of 2 times, substituting the 1 and the 0, would have 1 cubed divided by 3 minus 0 cubed divided by 3. And we can cross out the 0 divided by 3, of course, and we would have minus the square root of 2 times 1/3, and that can be written as minus the square root of 2 divided by 3. And this would be the result of the given integral.